What's going on, everybody? It's Mr. Gus, and we're back in the physics classroom. It's bright. It's a sun-shining day. We've got a bunch of toys in the physics classroom today. In particular, though, we're looking at conservation of angular momentum, okay? It's kind of our last stop in rotational motion, angular momentum, and the conservation of it. Again, conservation laws typically take place, or we utilize them when there are no external forces on our system. So we're going to look today and see an example of that and ask ourselves, are there external forces? And if the answer is no, we're going to go ahead and use our conservation laws to determine something that is unknown about our system. Let's look at our setup. I have over here our rotating platform that we've used. We use it for the chair. Typically we put the chair on it and it rotates, but if I take the chair off, now it just rotates freely, and there's a mark of tape on there for us to figure out how fast it is in fact rotating. Our job today is going to be to determine the mass of this thing after a collision takes place. I have no idea, and I've Googled it, I looked it up. So Pasco, if you're watching, tell me what is the mass of just the top of this rotating object. I don't really want to take it apart. I guess I could to find the mass of this disk, but I don't want to. So I want you to do it for me, okay? Unless one of you knows someone from Pasco. But otherwise, let's find the mass of this disk. Here's how we're going to do it. We've got to take some data after this thing makes an angular collision, before and after. Here we go. I got a disk. This disk is going to rotate. You should be able to figure out how fast it's rotating based on how fast that piece of tape is moving. As it rotates, we drop a heavy weight on it from not too high, and you notice that it slows down, okay? That was our experiment. Your job is going to be to go take data on that. So if you're watching this thing in times 1.75 speed or times 2 speed just to get through it fast, you're going to have to go back, slow it down, and get actual accurate time data. What data will you need? First question. Were there outside forces? I had this spinning disk. I dropped a heavy disk on it. Was there an outside force? Did I touch it? Did I slow it down? Did I do anything to change its speed besides adding mass to it? The answer is absolutely not. I didn't touch it at all. I just increased the mass. I changed the rotational inertia of the object. Because of that, the initial angular momentum is equal to the final angular momentum. Let's go ahead and start breaking down what we had here. This marker stinks. I'm changing markers again. So initially, with just the disk was rotating. So I have my inertia, rotational inertia of the disk times its initial velocity. It should be equal to the sum of both momentum, which is the disk's angular momentum and the mass's angular momentum. We're trying to find what you want to know. Our question mark is, what is the mass of the disk? We have no idea what it is. We need to find that. So let's go ahead and start expanding out these things. Well, I of a disk is 1/2 mass of disk. That's what I want to know. Times r the disk squared times the initial speed it was moving at equals 1/2 mass of the disk. That's what I want to know. Times r squared times the final speed plus the mass of the mass, which is also a disk, 1/2 mass of the mass times its radius squared times the final omega. All right, let's think about some things we could measure here. Now, I want to find this. I'm curious about the mass of the disk. That's what I'm looking for. It shows up on two different sides of my equations. And for those of you thinking, oh, it's going to drop out because it's on both sides. It's not going to drop out because I've got 3 terms. I've got my initial term, I have my disk after the collision term, and I have my mass after the collision term. So no, the mass of this object is not going to drop out. It's not in every term. It's in 2 of the 3 terms, which is good because I should be able to isolate it then and solve for it. What should I measure? Well, first things first, I'm trying to solve for disk. This I can measure with a meter stick. So the radius of the disk, that's a meter stick, no problem. How can I get the initial angular velocity? I'm going to have to go back, use the video data. Again, do not do the video in ×2 speed. It will not be accurate. Make sure you go back and watch the video in real-time speed and go ahead and find the initial speed. This is just change in theta over time. So pick a various number of rotations, time it, see how long it took. Okay? Moving along. The mass of the disk, still looking for that. The radius of the disk, it should be the same as before, but again, using a meter stick. I can find that. Final angular velocity, that's just going to be change in theta over time after the collision takes place. And that's the same as right here. Those things are rotating at the same time, in the same way, with the same velocity. Those two values are the same after the collision. Let's make a distinction that, hey, that's before, that's after. The mass of the mass, I can just like read that, just read it right off the mass itself. And the R, let's go ahead and also use the meter stick. Okay? So your job is going to be go back, watch the video, get some data on velocity. I will go ahead and give you the mass of the mass. It's 10 kilograms. And I will give you the radius of the disk and the radius of the mass itself. I will give you both of these while you go back and get your data from the video previously. Okay? So you go ahead and do that. I'll do this. Oops. 13 centimeters. Disk itself. $23. .23 meters. Okay. Here's what I got. The mass, 110 kilograms. The disk, 0.23 meters, and the mass has a radius of 0.13 meters. I've got everything that I need. I got everything that I need. Your job now is to go back and figure out what the mass of the spinning disk is. Now, it's going to be based on what you find for your velocities. I want you to go find your velocities. Here's the range it should be between. I should see a mass of the disk anywhere between. It should be in a range between 2 kilograms all the way up to like 4 or 5 kilograms. We'll say 4.5 kilograms. It should be closer to this end than that end, but anywhere in that range based on your angular velocity before and after the collision. So pay careful, close attention to that. The closer to 2 kilograms, the better. I'm not sure it's exactly 2 kilograms. Again, Pasco, if you're out there, send me an email or a follow and go ahead and give me an answer. But I think it's closer to 2 kilograms than anything else. Okay? This is a perfect example of conservation of angular momentum in an angular collision. We've got a collision, no outside forces, conservation of energy, or conservation of momentum. Energy is not conserved because you can hear it transforming into thermal or sound energy. If you got questions, drop in the comments, send me an email, ask me in class. Until next time, see ya.